Hello and welcome to our baby universe, its first 380,000 years. Lecture 3 in the 6-part lecture series, Cosmology, the Study of the Universe. My name is Fulvia Fiorani. Today's lecture is really the story of how all the fundamental particles that we and everything around us were formed in the very early universe. So the essence of this lecture is to answer two main questions. What was the universe like at its earliest moments, and how did all the matter that we see around us emerge from the initial extremely hot and dense state, which we call the Big Bang? To answer these questions, we will cover a time span that goes from just a tiny fraction of a second after the Big Bang to a time when the universe was only 380,000 years old. We will see that this is a very critical time in the universe's evolution. While we have a fairly good understanding of the universe from the first few seconds after the Big Bang, our understanding of the first fractions of a second of cosmic history is really no more than a very well-informed guess. Yet understanding this era is essential to understanding our universe. In our previous lecture, we saw the development of the Big Bang theory and then followed the evolution of the universe from the first stars to galaxies to the cosmic web, and learned how they formed in a hierarchical formation process through expansion and the action of gravity. In today's lecture, we will cover the evolution of the universe from a time extremely close to the Big Bang and up to the 380,000 year mark. For the period that we covered in the last lecture, we have an impressive amount of observations and measurements on which to rely. And this collection of data leaves us fairly confident that we understand this portions of the universe's history quite well. As we go farther back in time, however, our confidence begins to decline. We will see that as we get closer and closer to the Big Bang, our knowledge is little more than a very well-educated guess. We will see that the universe begins in an extremely hot and dense state. And as the universe expands and cools, cosmic change occurs incredibly fast during the beginning, then slows down as the universe's temperature and density decrease. Now please note that this image is a logarithmic scale. So the first of these two seemingly equal chunks of time represents the first 380,000 years, while the other represents over 13 billion years. So today we are really looking at a very tiny portion of the universe's history. The key concept for understanding this period in cosmic history is that as the universe expands and cools, things start to happen. From our last lecture, we should all feel pretty comfortable with the idea that the universe started to expand from an initial hot and dense state. As the universe expands, the density decreases because the same amount of stuff occupies a larger and larger volume. As the density decreases, so does the temperature. So if we go backward in time, the universe gets smaller and smaller, denser and denser, and hotter and hotter. So that within a tiny fraction of a second after the Big Bang, particles start to emerge from the extremely high concentration of energy. Now, temperature is directly related to energy. Temperature is simply a measure of the speed of particles, or a measure of their energy. The faster they are moving, the higher their energy, and the more violently they collide, releasing huge amounts of energy and creating new particles. By the way, that is what particle accelerators do. They accelerate particles to speeds approaching the speed of light and then smash them together to see what particles are produced in the collisions. The key to understanding particle creation or formation is that mass and energy are interchangeable, as we know from Einstein's most famous equation, E equals mc squared. Now this equation tells us that mass can be converted into energy and energy can be converted into mass. But for a particle to be created from energy, the energy must be greater than the particle's rest mass energy. In other words, the collision energy must be sufficient to make a new particle. In the beginning, when the universe was extremely hot, there was enough energy for all types of fundamental particles to be created. And as they collided with each other, they were continuously being destroyed and created. As the universe cooled down and the energy decreased, only the lightest of the fundamental particles were produced. These are the particles that make up all the ordinary matter in the universe today. So what specifically will we talk about in this lecture? We will start with a preliminary understanding of the fundamental particles that make up all the ordinary matter in the universe, and how these particles interact with each other through the four fundamental forces of nature. Then we start our progression from the beginning of time. A tiny fraction of a second after the Big Bang, the universe underwent an extremely rapid exponential expansion called cosmic inflation. After inflation, the universe stabilizes into a very hot, dense, and highly energetic quark soup. Amazingly, all of this happens within the first picosecond after the Big Bang. That's 1/1000th of a nanosecond. Within the first 3 minutes, the universe cools down enough for the first atomic nuclei of hydrogen and helium to form. Not much happens after that for the next 380,000 years. By that time, the universe has expanded and cooled down enough for the first neutral atoms of hydrogen and helium to form. And it is at this point that the universe becomes transparent for the first time, and light is able to freely propagate throughout the universe. This is the oldest light in the universe and holds a treasure of information about the early universe. As already mentioned, the key concept in understanding early cosmic history is that as the universe cools, things happen. In other words, the universe goes through phase transitions at specific times and temperatures. As the universe expands, its density decreases. Therefore, it cools down. Just like when you spray air from a can of compressed air, as the air inside the can expands, it cools down, and you can feel the can getting cold. As the universe cools down, it goes through changes in its form and properties as it reaches certain critical temperatures. Let's take a look at an everyday analogy. We look at water as a function of temperature. At room temperature, water is in its most common form of liquid water. As we increase its temperature, at some point it will start to boil and transition into its gas phase as steam. If we decrease the temperature of water, it will eventually freeze and transition to its solid phase as ice. Now, these phase transitions occur at specific temperatures. At 100 degrees Celsius, water boils, becoming a gas, and at 0 degrees Celsius, water freezes, becoming a solid. As we go along, we will see that the universe goes through a succession of phase transitions as it cools down. These transitions occur at specific times when the universe reaches certain temperatures and energies. So it's important to know the units in which we measure these quantities. Time refers to the time elapsed after the Big Bang, and it's measured in our familiar units of seconds, minutes, and years. Temperature is the temperature of the universe at key times during its expansion. It is measured in Kelvin units, which is the absolute temperature scale. Now, kelvins are similar to Celsius degrees, but they're offset by 273. And as a reference, 0 Kelvin, or absolute zero, is equal to minus 460 degrees Fahrenheit. Energy refers to the average energy of particles in the universe at a specific time. It is measured in giga-electron volts. The giga-electron volt is a common unit used in high-energy physics. Now, temperature and energy can be used interchangeably, since temperature is simply a measure of its energy. So we will most often refer to the temperature of the universe and not its energy. As we look back to tiny fractions of a second after the Big Bang, the universe is characterized by enormous temperatures, densities, and energies. And to make sense of these extremely small and extremely large numbers, we will have to use scientific notation. For those who are not very familiar with it, here are some examples. We start with small numbers of time. 10 to the minus 3 is equal to 1 divided by 1 followed by 3 zeros, or 0.001, also called a millisecond. 10 to the minus 6 is 1 divided by 1 followed by 6 zeros, or in its decimal form, also called a microsecond. 10 to the minus 9 is 1 divided by 1 followed by 9 zeros, or in its decimal form, also known as a nanosecond. So I think you get the picture. 10 to the minus 43 seconds is as far back in time as our current laws of physics allow us to go. It is 1 divided by a 1 followed by 43 zeros, or in its decimal form, which I did not have enough space to write. In other words, a very tiny fraction of a second. So now let's see the large numbers. 10 to the third is a 1 followed by 3 zeros. 10 to the ninth is a 1 followed by 9 zeros, commonly known as a billion or a giga, like gigabytes in computer lingo. And 10 to the 32 Kelvin is a 1 followed by 32 zeros, and it is the highest temperature that our current laws of physics can explain. So we start our look at the early universe by asking ourselves, what are the everyday things around us made of? In other words, what are the fundamental building blocks of matter? We will start this quest by looking at more complex systems and then reducing them to simpler things. Humans and animals are made of a collection of organs that work and fit together to make a body. So what are organs made of? Well, organs are made of a bunch of cells that interact with each other. Plants are also made of cells. So the next obvious question is, what are cells made of? Well, both animal and plant cells are made of organic molecules that fit together in various configurations. Now let's move on to inanimate objects. Water is made of a combination of the elements of hydrogen and oxygen that combine together to form an inorganic chemical compound. Mountains are made of rocks and minerals, which are simply elements combining together to form chemical compounds. And moving away from Earth, we have stars, which are made of mostly hydrogen and helium gases. So what are organic molecules, chemical compounds, and gases made of? Well, they are all made of atoms. So we know that the everyday things around us are made of atoms, but atoms are not the fundamental building blocks. So let us continue our quest. What are atoms made of? Well, atoms are made of a positively charged central nucleus surrounded by negatively charged electrons. Now, electrons are fundamental particles, but the nucleus is not. By the way, a fundamental particle is a particle that is not composed of other particles. The nucleus is made of protons and neutrons. The proton is a positively charged particle, and the neutron has no net electric charge. But protons and neutrons are still not fundamental particles. We can go even deeper. Protons and neutrons are made of quarks. Specifically, they are made of up and down quarks. The proton has 2 up quarks and 1 down quark, and the neutron has 2 down quarks and 1 up quark. As far as we know, quarks are fundamental particles. So quarks and electrons are the fundamental building blocks of matter. Let's see these fundamental particles in a chart. Here are our two up and down quarks, and here is the electron. As you can see, we have many more boxes to fill. Together with the electron, we have the electron neutrino. Now, neutrinos are nearly massless particles traveling through space with speeds very close to the speed of light. They very rarely interact with normal matter. In fact, there are trillions of solar neutrinos passing through each of us every second. Electrons and neutrinos are grouped as leptons. The up and down quarks have second-generation heavier cousins known as the charm and strange quarks, and a third generation of even heavier cousins called the top and bottom quarks. The second-generation cousin of the electron is the muon, with its associated muon neutrino, and a third generation, the tau particle, with its associated tau neutrino. These 6 quarks and 6 leptons are the matter particles. In particle physics jargon, they are called fermions. But we still have some boxes to fill. These next particles are the force carriers and are categorized as bosons. Matter particles interact with each other by exchanging force carrier particles. The gluon, very appropriately named, is the mediator of the strong nuclear force that keeps quarks bound together to form protons and neutrons. The photon, commonly known as the quantum of light or particle of light, is the force carrier of the electromagnetic force. And these are the W and Z bosons, which mediate the weak nuclear force and are responsible for radioactive decay of atoms. We have one remaining box to fill, and that belongs to the Higgs boson. Some of you may recall that the discovery of the Higgs boson in 2012 made worldwide news. It is the interaction of particles with the Higgs field that gives particles their mass. This discovery of the Higgs boson completed what is known as the Standard Model of particle physics, simply known as the Standard Model. The Standard Model describes all the fundamental particles and their interactions. Essentially, it is a mathematical framework for understanding almost everything in the known universe other than gravity. The Standard Model is considered the crowning achievement of 20th century physics. Now, only the first generation matter particles, the up and down quarks, the electron, and the neutrino, are commonly found in nature and make up all the ordinary matter in the universe. The heavier generation 2 and 3 particles are very unstable and quickly decay into the stable generation 1 particles. So why did we talk about all these other particles? Well, because in the very early universe, all these particles existed together in an ultra-hot soup of very energetic particles, constantly smashing into each other and converting into energy, which in turn converted into other particles, transforming over and over from one particle to another. As the universe cooled, the particle collisions did not have enough energy to produce the heavier particles, so only the lighter and more stable generation 1 particles remained. Now let's take a look at the 4 fundamental forces of nature. The force we are most familiar with is the gravitational force. It is a universal attractive force. Every particle feels the gravitational force according to its mass and energy. The gravitational force is also the weakest of all 4 forces. Gravity is a long-range force, although it gets weaker with distance. The mediating particle of the gravitational force is the hypothetical graviton. Although they are presumed to exist, our current laws of physics cannot actually predict their existence. The next familiar force is the electromagnetic force. It interacts with electrically charged particles. It is responsible for keeping the electrons bound to the nucleus to form atoms. And it is responsible for practically all of everyday phenomena, except for gravity. And just like gravity, it is a long-range force that decreases with distance. The mediating particle of the electromagnetic force is the photon, also known as a quantum of light. The last two forces are not as familiar. The weak nuclear force is responsible for the radioactive decay of atoms. In other words, the weak nuclear force allows one particle to change into another. The effective range of the weak force is limited to subatomic distances, and the mediating particles are the W and Z bosons. The last of the forces is the strongest one, called the strong force. It is 10 to the 38, that's 10 followed by 38 zeros, 10 to the 38 times stronger than gravity. It is responsible for holding quarks together to form protons and neutrons. And it is also responsible for holding protons and neutrons together in atomic nuclei. It is a very short-range force on the order of the size of a proton. That's about 10 to the minus 15 meters. The mediating particle is very appropriately called the gluon. Now, we mentioned earlier that as we go farther and farther back in time, the universe gets smaller and smaller, denser and denser, and therefore it gets hotter and hotter. At the extremely high temperature at the beginning of the universe, it is believed that all four forces were unified into one single force. Then at 10 to the minus 43 seconds, gravity splits off. Once again, this is scientific notation for less than a trillionth of a trillionth of a trillionth of a trillionth of a second. We cannot actually measure this time, but it represents a quantum gravity wall beyond which our current laws of physics break down. The long sought-for theory of everything aims to fully explain and unify all the aspects of the universe. Finding this theory is one of the major goals in physics. Once gravity splits off, the three remaining forces remain unified into what is called the grand unified theory. Although this unified force has not been directly observed yet, there are many models that theorize its existence. At 10 to the minus 35 seconds, the strong nuclear force splits off, and the two remaining forces are unified into what is called the electroweak interaction. Now, this unified force has been directly observed in particle accelerators. And finally, when the universe was just a picosecond old, the weak nuclear force and the electromagnetic force start to separate, so that by about 1 microsecond after the Big Bang, all of our four forces of nature take their current form. And here we are today. We have a very good understanding of how the four forces affect everything we know. Now, we shouldn't be too surprised by the fact that what seem to be separate phenomena today could be different aspects of a unified force. Up until the mid-1800s, electricity and magnetism were considered two separate phenomena. Then in 1864, James Clerk Maxwell unified the two into a single theory of electromagnetism, which is described by what are known as Maxwell's equations. Okay, now that we are armed with all of this preliminary knowledge, let us start from the beginning. In the beginning, there was a bang. Or was there? The truth is, we don't know what actually happens at t equals 0. Our current understanding of nature can take us as far back as 10 to the minus 43 seconds after the Big Bang, where we meet our quantum gravity wall. But it cannot explain why, how, or even if the Big Bang actually occurred. Before this critical time, the universe was too high in temperature, too high in density, and too small in size for our current laws of physics to describe. We call the time from t equals 0 to t equals 10 to the minus 43 seconds the Planck epoch. It is generally assumed that quantum effects of gravity dominate all physical interactions at this time scale. It is also assumed that all four fundamental forces are united as a single force. And it is hoped that a future theory of everything will provide us with some answers. So, for the moment, the answer to whether there was or was not an actual bang at the beginning of time is we don't know. The first period in cosmic history that we think we may know what occurred is a period called cosmic inflation. Most cosmologists believe that the universe underwent an extremely rapid exponential expansion of space in the very early universe. The theory was developed around 1980 to explain several puzzles with the standard Big Bang model. According to this theory, the inflationary period begins just 10 to the minus 35 seconds after the Big Bang. That's less than a trillionth of a trillionth of a trillionth of a second. Inflation lasted only a tiny fraction of a second, and for reasons that are not known, ended around 10 to the minus 32 seconds after the Big Bang. During this very brief period, the universe expanded at a rate faster than the speed of light and by a factor of 10 to the 26 in size. That's like taking a softball and expanding it to 3,000 to 4,000 times the size of our Milky Way galaxy in just a tiny fraction of a second. As the universe undergoes this extremely rapid expansion, it cooled down by a factor of 100,000. So what caused inflation? Well, the exact reasons for why inflation happened are still being explored. But a general consensus is that it was triggered by the separation of the strong and electroweak forces, which ended the grand unification epoch. And this occurred as the universe cooled down to 10 to the 27 Kelvin. Now, although most cosmologists believe that inflation occurred, there is yet to be found any observational evidence that it did in fact occur. So why are cosmologists so motivated to believe it? Well, because inflation solves problems with the standard Big Bang model, namely the flatness problem, the horizon problem, the structure problem, and the monopole problem. Let's briefly take a look at these problems and see how inflation solves them. We've already seen two in the previous lecture, but it doesn't hurt to see them again. The first is the flatness problem. Our observations indicate that on very large scales, the universe seems to be flat. Now, this is not the problem itself. This is a statement of the mass-energy density and the geometry of the universe. Recall that according to general relativity, matter-energy density affects the curvature of space with a specific critical value required for a flat universe. Cosmologists define omega as the ratio of the actual energy density to the critical energy density. Today, that value is extremely close to 1. Okay, so what's the problem? Well, the problem is that this condition is very unstable. So the conditions in the very early universe must have been even more fine-tuned, because any slight deviation would cause the universe to either expand so quickly that stars and galaxies would not be able to form, or cause the universe to recollapse very quickly onto itself. So inflation solves this problem by flattening out any initial curvature. The universe so rapidly expands that our small patch of the observable universe appears to be flat. Next is the horizon problem. Our observations indicate that on very large scales, the universe is homogeneous and isotropic. In other words, it looks the same from wherever you look and toward whatever direction you look. The horizon problem refers to communication between different regions of the universe. As we've seen before, and we will see again later, this is a map of the cosmic microwave background, the oldest light in the universe. It is seen from all parts of the sky to a very great accuracy to be at the same temperature. So the problem is, how does radiation coming from one point of the sky, 13.8 billion light years in one direction, know to be at exactly the same temperature as the radiation coming from the opposite point of the sky, also 13.8 billion light years away, when light would have to travel faster than the speed of light to get there? Inflation solves this by allowing a small portion of the universe that was small enough to achieve thermal equilibrium before inflation to exponentially expand and become large enough to include everything we see. So opposite sides of the universe that would otherwise not be able to communicate with each other can be at the same temperature now because they were at the same temperature before inflation. Next, we have the not so often mentioned structure problem. We saw in the previous lecture how gravity acts on tiny density variations to build the large-scale structure of galaxies, clusters, filaments, and voids. The problem is, the standard Big Bang model does not explain where these tiny density variations came from. The model simply invokes them as an initial condition. Well, inflation provides a mechanism for the generation of primordial density fluctuations. It is thought that inflation caused quantum fluctuations to be stretched out and become the tiny density variations we see in the cosmic microwave background today. And finally, the monopole problem. The grand unified theory laws predict the existence of magnetic monopoles. A magnetic monopole is a hypothetical fundamental particle with only one magnetic pole, either a north or a south pole. Now, the problem is no magnetic monopoles are found in nature. Now, inflation solves this problem by allowing magnetic monopoles to exist as long as they were produced before inflation. During inflation, the density of the magnetic monopoles drops exponentially, so their abundance drops to undetectable levels. Now, because inflation provides solutions to these problems, cosmologists believe that the universe underwent this inflationary period, even though it has not been observationally proven yet. Hopefully, the recently discovered gravitational waves will provide us with some more answers. After inflation, the universe continues to expand, but at a much slower rate. As it expands, the energy decreases, and it cools down, allowing the fundamental particles, or the building blocks of matter of which we are all made, to form. At a trillionth of a second after the Big Bang, we enter the quark epoch, and another critical phase transition occurs. The energy has decreased enough for the electroweak interaction to separate into the electromagnetic and weak force, so that all four fundamental forces have taken their current forms. But the energies are still too high for quarks to stick together. At this point, the entire universe was filled with an ultra-hot plasma known as a quark-gluon plasma. This plasma is made up of all the fundamental particles of the standard model, to include all the variety of quarks, leptons, and their corresponding antiparticles. Under these ultra-hot conditions, all these particles are constantly smashing into each other and converting into energy, which in turn converts into other particles. Within a trillionth of a second, the energy possessed by any given particle would have changed forms trillions of times. This ultra-hot, highly energetic state, in which we have quarks freely moving around and smashing into each other, is sometimes referred to as a quark soup. Now, although we very rarely mention antimatter in these lectures, let us take a small diversion and say a few words about it. One of the greatest unresolved problems in physics today is the matter-antimatter asymmetry. So first of all, what is antimatter? From what we currently understand, matter cannot be created without creating an equal amount of antimatter. Theory tells us that each ordinary particle of the Standard Model also has an antiparticle, or a particle with the same mass but opposite electric charge. For example, here is the negatively charged electron with its positively charged antiparticle, the positron. And here is the positively charged proton with its negatively charged antiproton. So what is the matter-antimatter asymmetry? Now, although we know antimatter exists because we can actually make it in particle accelerators, the universe contains matter, not antimatter. But why is that? Matter and antimatter should have been created in equal amounts, yet antimatter is not out there. Furthermore, when matter and antimatter meet, they annihilate each other. So if they were created in equal amounts, all of the matter would have annihilated, and we wouldn't be here today to ponder these questions. So some yet unknown mechanism or event in this very early period of cosmic history must have created a slight asymmetry between matter and antimatter, but it remains a mystery. So let us return to the quark epoch. The quark epoch ends around 1 microsecond after the Big Bang, when another critical phase transition occurs. Our next period takes us from 1 microsecond to 10 seconds after the Big Bang. Amazingly, from 1 microsecond on, the laws of physics that govern the behavior of matter are very well understood. By 1 microsecond after the Big Bang, the temperature and energy had decreased enough that the strong nuclear force could hold together 3 quarks to form hadrons, entering what is known as the hadron epoch. Our most familiar hadrons are protons and neutrons. As you can see here, protons are made of 2 up quarks and 1 down quark, while neutrons are made of 2 down quarks and 1 up quark. It is the strong nuclear force mediated by the gluon that holds these quarks together. Now, although the universe has cooled enough to allow quarks to bind together, it is still too hot and energetic at this time to allow protons and neutrons to bind together. Around 1 second, neutrinos cease to interact with matter particles and begin traveling freely through space. These neutrinos should still exist today and form what is known as the cosmic neutrino background. Unfortunately, their energies are too low for our present-day detection devices. When they are finally detected, they will provide direct information about our 1 second-old universe. At the end of the hadron epoch, the temperature has cooled such that hadron-antihadron pairs cannot be created. So most of the hadrons and antihadrons annihilate each other, leaving mostly electrons, neutrinos, and their antiparticles to dominate the mass of the universe. As the temperature continues to decrease, it reaches the point where electron-positron pairs cannot be created. So most electrons and positrons annihilate each other, giving rise to high-energy photons. Here is a simple animation of an electron-positron annihilation. We will see the 2 particles smash together and annihilate in a burst of energy. The photons produced during this period usher us into the photon epoch, when most of the energy density of the universe is in the form of photons, or radiation. Although these photons are still trapped in the very hot, young universe, they are the same photons that we will eventually see in the cosmic microwave background. So finally, the universe has cooled enough for the first atomic nuclei to form. In other words, for protons and neutrons to fuse together to form the first light atomic nuclei. The process by which they form is called Big Bang Nucleosynthesis. Let's look at the conditions in the universe right before Big Bang Nucleosynthesis. At the end of the hadron and lepton epochs, all the antimatter has been annihilated, leaving space mostly filled with photons. Now, because of the matter-antimatter asymmetry, a small amount of matter particles are left after annihilation. Now, small is a relative term. The number of matter particles is small compared to the enormous amount of particles during the quark epoch, but still big enough to form everything we see in the universe. Now, theory tells us that at this point, there is 1 neutron for every 7 protons. Before Big Bang nucleosynthesis, protons and neutrons have too much energy to bind together. But by 10 seconds after the Big Bang, the temperature of the universe had dropped down to about 1 billion degrees, which is cool enough for protons and neutrons to bind together through nuclear fusion, giving rise to nuclei of a few light elements beyond hydrogen. So we start with a ratio of 1 neutron to every 7 protons. A single proton is simply the nucleus of the hydrogen atom. 25% of the protons and all of the neutrons fuse to form deuterium, a heavy form of hydrogen. Deuterium is not very stable, and most of it quickly fuses to form the very stable nucleus of helium-4. A very small portion of the deuterium can fuse with a proton to form helium-3, and trace amounts of lithium-7 is also produced in the process. Now, Big Bang nucleosynthesis does not last long, just a few minutes, and by its end, the resulting matter by mass is 75% hydrogen, 25% helium, 0.01% deuterium and helium-3, and trace amounts of lithium-7. The brevity of Big Bang nucleosynthesis is important because it prevents the formation of heavier elements. And for that, we will have to wait for the next 2 lectures on stellar evolution. So let's test this theory. The theory of Big Bang nucleosynthesis gives us a detailed mathematical description of the production of light elements shortly after the Big Bang. Specifically, the theory yields precise quantitative predictions for the mixture of those elements, or their primordial abundances. The theory predicts that about 25% of all the matter after Big Bang nucleosynthesis should be helium, with trace amounts of helium-3, deuterium, and lithium-7. Of course, the remaining 75% is hydrogen. These curves are the predicted abundances of light elements, based on the number of protons and neutrons. In other words, this plot tells us that for any initial amount of ordinary matter in the form of protons and neutrons, as shown on the x-axis, we can make specific predictions of the abundance of light elements as shown on the y-axis that formed during Big Bang nucleosynthesis. So astronomers tested these predictions by observing objects in which very little stellar nucleosynthesis had taken place, and by observing very distant objects, therefore in the very early stage of their evolution. And indeed, their observations matched the predictions. The red circles represent the actual observations. Not only do they match on the curves, but they match for one specific value of protons and neutrons. So amazingly, Big Bang nucleosynthesis fixes the number of ordinary matter particles in the universe. In other words, we actually know how much ordinary matter was produced just minutes after the Big Bang. Not much happens after Big Bang nucleosynthesis for the next several thousand years. The universe continues to expand and cool, but it's still too hot for atoms to form. So we just have a whole bunch of photons, electrons, protons, and helium nuclei zooming around and bumping into and bouncing off of each other. Then around 50,000 years after the Big Bang, another phase transition occurs. The universe goes from being dominated by radiation to being dominated by matter. So let's take a look. On the horizontal axis, we have the cosmic size as the universe expands, with today being 1. And on the vertical axis, we have the density of the universe, with today being 1. As the universe expands, its average density drops because we have the same number of particles in a larger volume. So we have a decreasing line for matter density. Just like with matter particles, the average density of radiation particles, or photons, also decrease as the universe expands. But there's an additional effect. As the universe expands, the wavelength of radiation gets stretched by the expansion of space, therefore decreasing its energy even more. So the energy density of radiation falls off faster than matter, as we see here. The two lines cross around 50,000 years. Before this time, radiation is denser than matter. For example, 10 seconds after the Big Bang, matter is about as dense as the air we breathe, but radiation is 200 times denser than lead. Now, we haven't talked about dark energy in this lecture because its density is negligible compared to matter and radiation in the very early universe. But as we will see in the last lecture, dark energy is a property of space itself, and therefore it remains constant throughout the expansion of space. Now, as we see here, around 9.4 billion years after the Big Bang, the dark energy and matter lines intersect, and dark energy becomes the dominant component in the universe. Based on this, cosmologists divide cosmic history into 3 broad eras. First, the radiation era, when radiation is dominant, then the matter era, when matter is dominant, and finally the dark energy era, when dark energy is dominant. So let's take a look and see where we are today. So we live during the dark energy era, and that's pretty exciting because we know so little about it. Not much happens between 50,000 and 380,000 years. The universe continues to expand, and although temperature continues to drop, it is still too hot for atomic nuclei and electrons to bind together to form atoms. However, if we could have been there, we would have been bathed in a very beautiful light. After 50,000 years, the temperature had dropped to 10,000 Kelvin, which corresponds to blue on the visible light spectrum. By 380,000 years, the temperature dropped to 3,000 Kelvin, which corresponds to orange. As the temperature drops from 10,000 to 3,000 Kelvin, the color of light goes from blue to orange. This is an animation of the changing colors of the universe as the temperature drops from 10,000 to 3,000 Kelvin. We will see the colors of light slowly slip through a rainbow sequence from blue to green to yellow to orange. So let's take a look. So at 3,000 Kelvin, we would have been bathed in a beautiful orange glow. Of course, as the universe continues to expand and cool, the light shifts to red, then infrared and beyond, which we are not able to see with our eyes. Today we are still bathed in this light, but we cannot see it because cosmic expansion has stretched it into the microwave frequency. Although we cannot see it, we can detect it. And that is what we call the cosmic microwave background. But more on that in a couple of slides. So let's go back to our 380,000-year-old universe, and a very critical transition occurs at this temperature. After 380,000 years of expansion, the universe has cooled down to 3,000 Kelvin, or about 5,000 degrees Fahrenheit. So let's review the conditions right before the universe reaches this critical temperature. The universe is a hot plasma of photons, electrons, protons, and helium nuclei. Their energies are too high for them to stick together, so they're zooming around and bouncing off of each other. In particular, the photons, recall photons are particles of light, are scattered as they collide with free electrons. So the universe is opaque at this time. In other words, because photons cannot travel far before being scattered away by electrons, light cannot travel freely through the universe. Okay, so what happens at the critical temperature of 3,000 Kelvin? At this temperature, the universe has cooled down enough for electrons to bind to nuclei and form the first electrical neutral atoms of hydrogen and helium. Before this time, energetic photons would simply blast away electrons as they tried to bind with nuclei. But now, photons no longer have the energy to ionize hydrogen, so the electrons can settle in and bind with nuclei to form neutral atoms. For historical reasons, this period is misleadingly called recombination, even though electrons and protons had never combined before. Since electrons are now bound to nuclei, they are no longer freely moving around, so photons are no longer scattered by electrons, allowing photons to now freely travel the universe unimpeded. In other words, the universe becomes transparent for the first time. This is the oldest light in the universe and has been propagating ever since. We see this same light today as the cosmic microwave background. We cannot actually see it with our eyes because it has been redshifted into the microwave spectrum by cosmic expansion, but we can detect it. So what is the cosmic microwave background? As we've just mentioned, it is the oldest light in the universe. It is the leftover radiation of the Big Bang and is spread almost exactly the same throughout the universe. Essentially, it is a snapshot of our universe only 380,000 years after the Big Bang. These photons are by far the greatest body of information we have about our universe's past. Therefore, analysis of the cosmic microwave background allows cosmologists to probe the physical conditions and properties of the very early universe. The first thing that it shows us is that at this age, the universe had a very high degree of uniformity. In other words, the universe was very much the same throughout. This also explains why on very large scales today, the universe looks the same in all directions. Today, the temperature of the cosmic microwave background has been very precisely measured throughout our entire observable universe to be 2.725 plus or minus 0.002 Kelvin. That is an amazing degree of uniformity. The existence of this radiation and its uniformity in temperature is proof that the universe started out in a hot, dense state and then cooled down as it expanded. The colors that we see in this map simply represent tiny temperature and density variations on the order of 1 part to 100,000. As we saw in the previous lecture, these tiny density variations are the seeds of galaxies and clusters of galaxies we see today. The cosmic microwave background and its detailed pattern of temperature variations is truly a treasure trove of information about the universe's youth, revealing to us everything from the amounts of atoms, dark matter, and neutrinos that are present in our universe today to the large-scale geometry of space itself. Hidden in this pattern of radiation is a complex story that helps scientists understand the history of the universe both before and after this radiation was released. So by analyzing the temperature and density variations in the cosmic microwave background, we can decipher vital statistics about the universe. Let's briefly see how the detection of the cosmic microwave background has improved through the years and how it has changed the values of important cosmological parameters. This is the first all-sky map of the cosmic microwave background, as seen by its discoverers, Penzias and Wilson, in the mid-1960s. In this map, we see a constant temperature of 3 Kelvin, which is very close to absolute zero, so the universe is a very cold place today. Now, the white line is simply the plane of the Milky Way. COBE, or the Cosmic Background Explorer, was the first satellite to show slight temperature variations and hints of cosmic structure never seen before. This map can be regarded as the starting point for cosmology as a precision science. WMAP, or the Wilkinson Microwave Anisotropy Probe, was the next probe. As the sensitivity of instruments increased, so did the data. Data from WMAP set the age of the universe at 13.75 billion years old, and the percentages of the constituents of the universe as seen listed here. And here is the most current image from the European Space Agency's Planck satellite. This is the highest precision picture of the cosmic microwave background. Once again, as the resolution of instruments gets better, so does the data. We will talk more about this current set of data in the last lecture in this series. So let's briefly review the cosmic epochs and events that created and formed all the particles of which we and all the universe we see around us are made. We will see that as the universe expands and cools, specific events occur at critical temperatures, and that these events occur very quickly at first, then slow down as the universe expands. We start with the Big Bang. This is our time equals 0 event. But we really don't know anything about the bang itself. We don't know what banged, we don't know how or why it banged, and we certainly don't know what happened before it banged, if it banged at all. The Planck epoch is our current limit of the laws of physics. So we really don't know what happened during this time. It is assumed that any physics is governed by the quantum effects of gravity. It is believed that all 4 fundamental forces of nature are unified as a single force, and that the Planck epoch ends when the force of gravity separates from the other forces. Our next event at 10 to the minus 35 seconds is inflation. Although not yet observationally proven, it is believed the universe underwent an extremely rapid exponential expansion that only lasted a tiny fraction of a second. Inflation solves problems with the standard Big Bang model and provides an explanation for the primordial density fluctuations which gravity will eventually act upon to form galaxies we see today. At about a picosecond after the Big Bang, we enter the quark epoch. And from this point on, our physics is pretty solid. Our largest particle accelerators can actually achieve these conditions, so we can study them very well. So during the quark epoch, all fundamental particles of the standard model that we saw at the beginning of this lecture are constantly being created and destroyed. Their energies are too high to bind together, so we have a very hot and dense state of freely moving fundamental particles zooming around and smashing into each other. We refer to this as a quark soup. By 1 microsecond after the Big Bang, all the 4 fundamental forces have separated into their current forms, and the temperature has dropped enough for quarks to bind together to form protons and neutrons. So all the protons and neutrons that make up our universe were formed just 1 microsecond after the Big Bang. However, the temperature is still too high at this stage for protons and neutrons to bind together to form nuclei. And for reasons that are not yet known, a slight matter-antimatter asymmetry results in the elimination of antimatter. By 10 seconds, most of the electrons and positrons also annihilate, producing an enormous amount of photons and ushering in the radiation era. Around 1 minute after the Big Bang, the universe cools down enough for protons and neutrons to bind together and form the first atomic nuclei. The process by which they form is called Big Bang Nucleosynthesis. At the end of Big Bang nucleosynthesis, ordinary matter in the universe is 75% hydrogen, 25% helium, and trace amounts of other light nuclei. Finally, at 380,000 years after the Big Bang, the universe has cooled down enough for electrons to bind with nuclei to form the first neutral atoms of hydrogen and helium, with which we are all familiar today. Now that all the electrons are bound within atoms, photons can freely travel, and the universe becomes transparent for the first time. We see these photons today as the cosmic microwave background. It's amazing how much we know about the very early universe, but many puzzles still remain. One of the puzzles is dark matter. The most fundamental question about dark matter is, what is it? And did it form in the very early universe? Despite decades of research, the nature of dark matter still remains unknown. The next mystery is matter-antimatter asymmetry. Our current laws of physics predict that matter and antimatter should be produced in equal amounts. During the Hadron Epoch, matter and antimatter annihilated. While all of the antimatter was annihilated, a small amount of matter survived. The mystery is, why is the universe today made entirely of matter? Or going back in time, why did the universe start out with more matter than antimatter? Then we have inflation. We still know very little about it, how it started, or why it came to an end. Although most cosmologists believe inflation occurred, we do not have any observational proof, so we really don't know if it happened at all. As we go back in time, we eventually hit a quantum gravity wall at 10 to the minus 43 seconds after the Big Bang. The very nature of space and time was unlike anything that exists in our universe today. Our current laws of physics break down at these conditions and cannot provide us with a description of the universe. Maybe a future theory of quantum gravity will provide us with some answers. All indications so far are that solutions to these puzzles lie in the first fractions of a second after the Big Bang. These earliest moments may have included events and interactions or forms of matter and energy that we still know nothing about. This is why understanding this era is the essential key to understanding our universe. The next lecture in this series is The Birth, Life, and Death of a Sun-like Star, Part 1 on stellar evolution. In today's lecture, we saw how the first elements of hydrogen and helium formed shortly after the Big Bang. But all the other elements found in nature are produced by stars during their lifetimes, and then disperse the elements throughout the universe as they die. In this first lecture on stellar evolution, we will see how and where stars are born, how they live out their stable life phase, and how an average star, such as our Sun, will die quietly, shedding its outer layers as a beautiful planetary nebula, then slowly fading away as a white dwarf. I hope you've enjoyed today's journey into our very infant universe. Hope to see you next time, and thank you for watching.